Let's see. Okay, it says it's streaming. Okay, so for those of you who check the video on Tuesday, there seems to be some bug around OBS making that our Monday video was short. So yeah, it was cut short. So only on the introduction part. So sorry about that. I'm still trying to figure out how OBS work on situations. But today we are not changing slides, so it should be fine. And anyway, any question on what we talk about on Monday? And also we will have a short review. Okay, so another mistake we made, if I go over a review, is that, wait, shit, I'm wrong thing. Okay, so I'm using this so we can change, right? Okay. So another mistake was on the slide was this B part. So when B is bigger than 0 is advanced and B less than 0 is delayed. So we have this in reverse order on Monday. And anyway, a quick review. So let's see. Maybe start at the very beginning. The review. Wait. Yeah, we are talking about signal and the system. And once again, signal is a function like this, x of t. And the system we haven't seen, but it's going to make something that maybe one signal to another signal. So maybe input signal to output signal, and the system is this tiny arrow in the middle. And usually we're expressing things like we'll write x of t to y of t, or even omit this, but we'll write y of t equal to some relation to x of t, like y of t equal to dx dt. And anyway, we start talking about properties of signals, and those are easy. So let's jump to more non-trivial part. So we are talking about three transformations on signals. So there's basically some transformation on the time parameter. We are all thinking about one-dimensional signals right now. So there are time shift, time reversal, and time scaling. And just like what they said, so time shift means you add or subtract something on this time variable, time independent variable, and you will either delay or advance your signal. Yeah. So see, this is a delay signal, it shift to right, and this is an advanced signal, it shift to the left. And time reversal means you add a minus sign on this time variable, and you will flip the signal, flip around left and right around this time equal to 0 axis, like this. And there's time scaling, that is you multiply time by a number, and you will either squeeze or stretch out your signal, once again around this time equal to 0 axis. And now this one is a little tricky to define on the discrete time signal, because discrete signal are always spaced out with integer values. So if you are multiplying by another integer value, then that stretching is not quite well defined. But let's ignore that for now. And we talk about how to compose different time transformations. So for example, here we have an example of time shift combined with time reversal. And we see that you need to be careful about the ordering of the operation. So here you need to remember that every time you do an operation, you are operating on this time t. So here you should add +1 to your t first, then add this minus sign, and you will get the signal you want. And if you are doing the transformation in wrong order, you will get the wrong signal, because that's not what you want. Okay. And here's another example where you're composing the time scaling and the time shift, and once again you need to do this in correct order. Okay. And yeah, that's it. Any questions on the review? Otherwise, let's go to other topics. Okay, other topics. So this is basically what we do today. talk about the periodic signal and different kind of periodic signal and their properties. And this will also be a very important concept throughout the whole class. Okay, yeah, and analysis of different periodic signal. So what is a periodic signal? Well, here is a very intuitive pictures. So a periodic signal is basically a signal that repeats itself from minus t infinity to plus t infinity. So for continuous time periodic signal, it's like this. So we have a signal like this, and it will keep repeating itself all the way to t infinity, and also repeating things from time past infinity. And if it's discrete, then it's the same concept. You have a signal, so now it's like a three dot repeating signal. So this minus 1 plus 1 plus 1 pattern keep repeating itself, and from t minus infinity, now it's n, from n minus infinity to n plus infinity. Yeah. And if you want to write this in mathematical form, it means that there exists some big T. So for continuous time, there exists some big T, such that your signal x of t will equal to signal x of t plus big T. And remember, this is a time shift. This is a time shift of x of t. So it means that you take this whole infinite long sequence, and you shift everything to, I think, to the left, to the left with distance big T, and it doesn't change at all because it keeps repeating itself. So we'll shift this shape to this shape, and this shape to this shape, etc. And this whole infinite long sequence will match itself after you're doing this shift. Okay, so there is some big T, which we'll call period, such that x of t equal to x of t plus big T. Then this signal is periodic. And yeah, and similarly, for discrete signal, there exists a big N, such that x of n equal to x of n plus big N. And let's emphasize this once again. So when we write this, it means that these two functions are totally equal. This means that these two functions match at every value of big T, of small t, and those two functions matches at every value of small n. Okay. So yeah, so you do the shift by a period, and the signal doesn't change at all. And we didn't quite write here, but it's easy to see that for discrete signal, this bigger need more constraint because discrete signal only have value on integer values, so this bigger also need to be integer. Okay. Okay. Question? No, I think this is still pretty intuitive. Okay, so this is a mathematical definition of periodic signal. There are signals that satisfy those relationships. A signal, and as we said, a periodic signal is unchanged by time shift of one period, so big T or big N. And another interesting thing about this property. So if you shift T, it doesn't change. Then you shift big T once again, it should still not change. So maybe look at the picture. So shift everything to left by one slot, it doesn't change. Then you shift to the left by two slots, it doesn't change. Or you shift to a plus by one slot, plus by two slots, it doesn't change. Okay, so that means that if you instead of use big T here, you use big 2T, 3T, 4T, the signal still doesn't change. Okay, so you can if it's periodic with period big T, it's also periodic with period big 2 big T, 3 big T, or 4 big T, etc. Or the integer value of big T, they are periodic. And similarly, that's also the same for the discrete time signal. So you can have a big N, then you also have periodic in 2N, 3N, 4N. Okay. And just too many periods. So we want to talk about a period of one signal. Then there is only one of them that's very important. That's the smallest one. Okay. So we call the smallest one the fundamental period, because if you know the smallest big T, then you also know all the bigger period. Those 2T, 3T, 4T, they are also all they are just integer multiple of T. So we only want to check the most important one, that's the smallest one. So the smallest big T or big N, we call it the fundamental period. And also another thing we kind of gloss over, that is this relation is satisfied, then it also satisfies for T less than 0, some T less than 0. So you can also have negative T here. This is also satisfied because it matches if when you shift left, it also matches when you shift right. But to make things simpler, we also only define our period for positive number. Okay, so yeah. So we only take T for bigger than 0 and N bigger than 0. And so our period are always a positive number. And our fundamental, so we take our period and the fundamental period always as positive number. So those are periodic signals. They always have the fundamental period. And if you cannot find the fundamental period, then the signal is just called a periodic signal. Or if the signal is just doesn't satisfy the relationship for any T, then it's aperiodic. Okay, so that's just a name. Okay, and once again, fundamental period is the smallest period of your signal, and the period of a signal is T or is the big T or big N, such that these relations is satisfied. And this fundamental period concept is something you need to remember throughout the whole class. I guess that's say this sentence once again. The smallest such big T and the big N is called the fundamental period. Okay, so let's go into an example. And we have 3 signal here. So x1 is of t is cosine of t, and intuitively it is very periodic, because as you know from I think high school trigonometry, this thing is periodic with period 2 pi, because when you go from cosine t to cosine t plus 2 pi, it's the same function. And you can convince yourself maybe by drawing a picture, so cosine kind of look like this. Although this is, cosine kind of look like this going up and down, and you know this distance is 2 pi. So you can convince yourself that this 2 pi is the smallest possible value, such that cosine t equal to cosine t plus 2t. Sorry, cosine t plus big T. And the 2 pi is the fundamental period, and the cosine is periodic. And also similarly for sine. So if signal x2 is sine of t, then this is also periodic with fundamental period 2 pi. Yeah. And now the interesting part of this question is, if you kind of stick together the cosine function and the sine function. So if we define this really weird looking function, that is cosine when t is less than 0 and the sine when t is bigger than 0, then what's the fundamental period of this thing? The answer is there's no fundamental period, because this is not periodic. I guess. So anyone want to say why it's not periodic? Well, I guess we can just look at this picture. So if it is periodic, then you need to be able to shift this thing and make it not change. But this picture has a very weird part, right? So this part looks very weird. It's a place where you are trying to stick together your sine and cosine. And that's just not happening on any other place. So if you shift the signal level right, then this will not match anything else. So this is not periodic. Okay? Yeah. Okay. Erase this. Okay. So that's periodic function and fundamental period. Okay. Now let's jump to, if there is no question on this, let's jump to a slightly different concept. So there are even and odd signals. And well, we start with mathematical definition. So even function is a function such that when you do time reversal, then the season doesn't change. So it has like a symmetry under time reversal. And in more detail, x of max t. So you flip the signal left and right, then it should be still the same signal. Or the similar thing when you are discrete signal. So here is an example of an even function. You see it's symmetric under around this n equal to, no, sorry, t equal to 0 line. So if you try to flip it left and right, it's still the same thing. And it's called even because if you think about polynomial function, so x equal to t to some power, and if you have even power, then the same signal will be an even signal. Okay? So for example, x equal to t squared, is 2 is an even function, sorry, is an even number, then this is an even signal. And so there's even, then there's odd. So odd signal is not totally symmetric, not totally invariant under this time reversal change, but it's still very symmetric around t equals 0. So when you do this time reversal, x of x changes to x of minus t, then it becomes minus of x of t. So a picture of that phenomenon is this. So when you flip left and right, then the signal also flipped up and down. Or you can think about if you are rotating around this 0 point by 180 degrees and the signal doesn't change. Okay, so it's a different kind of symmetry. And anyway, so those are our signal, and similarly for discrete signal, you just define as x of minus n equal to minus x of n, and that is called odd because they are like they are what the polynomial with odd power behave. So you have x equal to t cubed, it will be an odd signal. Okay, and here we have a better picture. So when you flip this odd signal left and right, then you see you get a minus sign. So you get flip up and down. Okay, question about the definition of even and odd signal. Okay, that's your definition. Okay, now something more interesting. So even odd signal are very special. If you draw an arbitrary signal, it's probably not even or odd. But we can always analyze any signal in as the even part and the odd part by doing this. So we can always separate our arbitrary signal into the even part and odd part by defining those two functions. So we have our signal and the time reversal of a signal, and if we add them together, then this and so add together divided by 2, so averaging over those two. So that's actually an even signal because if you take a time reversal, then xt go to x minus t and the x minus t go to xt, but addition doesn't care about order. So this is still the same signal. So this is even. And similarly, we can define the odd part of a signal as this difference between x of t and x of minus t. And you can see this is the other function because you take t to minus t. So this xt becomes x of minus t, x minus t becomes xt. And yeah, then you get a minus sign. So we define the even function out of whatever function and the odd function out of whatever function. And the cool thing is you add those two things together. So you add those two lines together. Then you find out that you go back to x of t because this plus x of minus t and the minus x of minus t just cancel out. So you can always write your signal as a linear combination of even part and the odd part. Okay, and that's pretty cool. So here's the picture that gives you some intuition about the decomposition. So we have whatever signal here. So x of n actually is a very special signal. For now, let's just look at this. This signal is not symmetric. So you just look at this. So it's 1 starting from 0 and 1, 1, 1. So it's 1 when n is greater or equal to 0, and 0 for all the negative n. Okay. Then when we do time reversal on this, then we'll flip around this n equal to 0. So the 0 parts, so this excuse me, n equal to 0 and x equal to 1 still stay the same, but left and right flip. So instead of 1, 1, 1 on the plus part, you have 1, 1, 1 on the negative part. And so what's the even part of this function? So you add those two together and divide by 2. Then on the negative part, you have 0 plus 1 divided by 2, so 1 half, 1 half, 1 half. And on the exact 0 part place, you have 1 plus 1 divided by 2, so it's still 1. And on the plus part is this 1 half, 1 half, 1 half. And you see that this is an even function now, because you flip around 0, then it doesn't change. It's 1 half, 1 half, and this 1 half, 1 half are the same thing. And what about the odd part of this function? So it's this thing minus this thing divided by 2. Then the 0 part, then at n equal to 0, it becomes 0 because 1 minus 1 equals to 0. And on the plus side, now we will have 1 over 2. And on the negative side, we have a negative of those divided by 2, so we have negative 1 over 2. And now you see this is an odd function, because if you flip left and right, then you got the minus sign because you now have this plus 1 half and minus 1 half. Okay, when you flip this signal left and right. Okay, so we'll check that. We can get the even function and get the odd function. Then also we add those two functions together, which will get back to this. And that's correct because n less than 0, we have 1 half plus minus 1 half becomes 0. And n equals 0, we have 1 plus 0 equal to 1. And on the plus part, we have 1 half plus 1 half equal to 1. Okay. So we can always decompose the signal into even and the odd part. Question? No. Okay. And that's about how much we will talk about even the odd part for today. Now we're going back to more about periodic functions. But actually the title is about exponential and sinusoidal signals. But you will see that this is a lot about periodic functions. But for now, let's get a review on complex number, because we are going to use a lot of them today. So I'm not sure which course do you take to learn those. I guess in high school you learn those, and probably also in calculus a little bit. But anyway, here's a review of complex number. So complex number is the extension of a real number, and it has a real part and the complex part. Okay, so we write our complex number as the real part sigma plus imaginary part j omega. Okay, and the complex number symbol here is j, that equal to square root minus 1. And this might be a little different notation from what you learned before, because sometimes people use I here, but we are a pretty engineering course today, and I sometimes stands for current, so we use J for the imaginary number. Okay, so J is square root minus 1. Oh, okay, and I might make some mistake in the slide, but so correct me when I use I instead of J in some part of the slide. Yeah, but the convention for this course should be the complex number, you use J here. Okay, and since the complex number have two parts, we express this we often express it as a dot in a two-dimensional plane. So we have this real axis and the imaginary axis. And so this sigma omega point represents this complex number z equals sigma plus j omega. Okay, and now more interesting thing. And there are two different representations of complex number we will use in the course. So there is this real and imaginary part. But since we are drawing this two-dimensional plane, we also express this in polar coordinate. So to express this point, we can, so the sigma and omega are kind of like the x value and the y value. But we can also express this point as polar coordinate, as we can recall down this length to origin, this r value, and this angle theta here. Okay. And then there will be a transformation back and forth between this Cartesian coordinate and the polar coordinate. So here we see one of the transformation already. So if we know r and the theta, so the transformation between sigma and omega and r and theta. So if we know r and theta and want to calculate sigma and omega, then we can just do basic trigonometry. So sigma will be r cosine theta, because that's how cosine theta is defined, and omega will equal to r sine theta. Okay. And okay, so that's one way. And what about we know sigma and omega, and we want to know what are the r and theta? Well, then r will equal to square root of sigma square plus omega square, because the triangle equation here, sorry, Pythagorean equation here. So r square equal to sigma square plus omega square. So r just equal to square root of sigma square plus omega square. And what about theta? Then theta we can learn also from trigonometry. And there are several ways to define this, but usually we do this theta equal to arctangent of omega divided by sigma. So tangent theta will be this omega divided by sigma. And then you can calculate theta from this arctangent. Okay? Question? Okay. You should be all pretty familiar with this. Okay. Now, things you might be a little less familiar with, now these are things you should learn in calculus, is this Euler relationship. So, the proof you can go back and check the textbook, but there is the relationship that e to the j theta equal to cosine theta plus j sine theta. Okay, and yeah. So this is kind of related to this change back and forth between between Cartesian and the polar coordinate. So you can see this e to the j theta as representing this complex number z in polar coordinate. I guess for when r equal to 1. Okay. And so when I equal to 1, then this e to the j theta will equal to this z, and the cosine theta will be the real part, and the j sine theta will be the imaginary part. Okay. And okay, so here we have the Fourier relationship. So we can express z in either sigma and plus j omega, and sigma will equal to r cosine theta, and omega equal to r sine theta. And this whole thing will also equal to r e to the j theta. So yeah, so if we want to express so you can see that if we have a complex number and we know the r and the theta, then we can write it as r e to the j theta. Okay. So this is the polar decomposition of complex number. Okay. And here we have another thing that we'll use today and throughout the course. That's kind of not so much related to complex number, but it's a reverse of Euler's relationship. So we can see Euler's relation as expressing this complex exponential, so this e to the j theta as cosine theta and sine theta. But we can kind of reverse it and express cosine theta and sine theta as complex exponentials. That is by noting that if we have e to the minus j theta, then we have minus theta here, then this becomes cosine theta minus j sine theta. Okay? And now if we just add those two equations together, divide by 2, then we see that cosine theta equal to, okay, so here is where I have typo. So you need to j here. Okay? Let's use this. Okay, so cosine theta will equal to e to the j theta, oh, where am I? E to the j theta plus e to the minus j theta divided by 2. And similarly, you can take the difference of those two equations, and you see that sine theta equal to e to the j theta minus e to the minus j theta divided by 2, divided by 2j. Okay. So yeah, so you can also decompose cosine theta and sine theta back to linear combination of e to the j theta and e to the minus j theta, and that will be pretty useful as we'll see today and throughout the course. Okay, any question? Oh, we're very fast. We can probably teach more than expected. Okay, another question. Then, okay, let's go back to actual textbook material. Okay, now we talk about our complex exponential signals. Okay, and let's start with the continuous time case. And oh, okay. Okay, so continuous time complex exponential signal. And as you say, it's an exponential signal, so we have this e to the alpha t here. And also we have another constant in front because why not? So in general, a continuous time complex exponential signal is like this: x of t equal to c, that's some constant, and this exponential part e to the at. Okay. And as we say, it's a complex exponential, so c and a in general are complex. Okay. And well, we'll later see that we want to express a in the Cartesian coordinate and c in the Poynting coordinate because this makes analysis easier. But anyway, for now, let's try to see how these things behave. And let's start with the special case. So special case 1, when those are real, then this behave as the exponential function you are probably more familiar with. So if they are real, then it's an exponential function that either has exponential growth or exponential decay. Okay. So they are both real. Then a bigger than 0, then you have this exponential growth function. And if a less than 0, you have this exponential decay function. Okay? So that's one of the behaviors this complex exponential can have. But actually we care more about the quite opposite signal. Okay? So we care about periodic complex exponential and sinusoidal signals. So when this complex exponential being periodic, well, this obviously is not periodic, because if you shift this thing, well, doesn't look like itself. Shift this thing doesn't look like itself. So when it is periodic, is when A is purely imaginary. And this is kind of why we want to write A in this Cartesian coordinate. So I want to write A in the real part and imaginary part. Now, imagine A is purely imaginary, so A just equal to j omega. And for technical simplicity, assume your C is not 0, because C is 0 is really boring. X of t just equal to 0. Okay? So let's assume C not equal to 0, and our complex exponential will equal to x equal to c e to the j omega t. And for reasons, we also call this omega 0 instead of omega. Okay? Because that's kind of the convention, because this omega is going to be important. So we give it a subscript to show that it's special. And anyway, so our A is purely imaginary, so A is now this j omega naught. And we claim that this is periodic, because we can now solve our periodic equation. Now, hopefully you still remember at the start of class, periodic equation means we shift this to x of t plus 2t, t plus big T, and it should be the same thing. And if you plug in this, then the equation we want to solve will look like this, right? So x of t equals to this c e to the j omega naught t. Nothing happened, we just write it down. And x of t plus big T, well, we just change t to t plus big T. So we have c e to the j omega naught t plus big T. Okay? So we want this thing equal to this thing. And now is where we want to use this c not equal to 0. Because c not equal to 0, then we can cancel the, okay. So let's change this to a pen. Okay, so let's do this. It's not quite Blackboard calculation, but PowerPoint calculation. So c not equal to 0, so we can cancel c on the both part. Now we have e to the j omega t, e to the j omega small t plus big T. And so this whole part can also cancel with this small t here, right? Because the exponential of two things adding together is this times this. And so this part now become 1, and this part we left with e to the j omega t, big T. Okay? So those are pretty simple arithmetic. And okay, so if we want this thing to be periodic, then this needs to be satisfied. And can this be satisfied? There are now several cases. Okay, so our first case is super periodic. So when we have this singular case that omega 0 equal to 0, then we look back, our signal like this. Then the omega 0 equal to 0, then what you have the exponent here is just 0, and the e to the 0 is just equal to 1. So your x of t just equal to c. And there is a constant function look like this. And pretty easy to convince yourself that constant function is indeed periodic. Actually, it's periodic for any t, because you shift any value, constant function is still a constant value. It's still a constant function. Okay. So now that's very periodic, although it's fundamental period is kind of undefined, but whatever. It's a special case. And okay, so now more regularized case is when omega not equal to 0. Okay, now when when omega 0 is not equal to 0, then the fundamental period is something we can actually solve for. And now we want to see what's the smallest possible big T. Yeah, use. What's the smallest possible big T to make this equation correct? And we kind of ski over, but you need to remember that ski over the detail, but we remember that e to the, so when is e to the something equal to 1, thus I think this is also called Euler's relation, but we know that e to the 2 pi j equal to 1. Okay? And the 2 pi is the smallest possible value for smallest possible non-zero value for these two holds. Okay? And yeah, so we compare this to this, then we realize that this omega not 0, if we want to make this whole exponential equal to 1, then the smallest possible omega 0 t it should be 2 pi. Right? So yeah, so the fundamental period should be, so this big T should be 2 pi divided by omega. And but I gloss over a little detail. That is, we want the T to be greater or equal to 0. Okay? We want the T to be a positive number. And omega naught can actually be a negative number. And when that happens, then you actually use negative 2 pi instead of 2 pi here. And your T naught should be 2 pi divided by the absolute value of omega naught. So this is just swiping things around a little bit where omega naught is negative. And anyway, this is your fundamental period, because you want this thing to be a multiple of 2 pi, and the smallest possible one is this thing. Okay. So the smallest possible and the positive t is this thing. T naught equal to 2 pi divided by absolute value of omega naught. Okay. And just as we say, so we have an absolute value here. So e to the plus j omega naught t and e to the minus j omega naught t has the same fundamental period. Because when we calculate fundamental period, it's always a positive value, and we don't care about this omega naught being positive or negative. Okay. Question? Look at this one more time. Fundamental period T naught for complex exponential function is 2 pi divided by absolute value of omega naught. Okay, important equation. Okay, now let's look at another signal we talked about in the title. So sinusoidal signal basically means signals that look like sine or cosine. You can see the sine here. Okay, so sinusoidal basically means look like sine. Okay. And sinusoidal signals are closely related to complex exponential, as you probably get a hint when we talk about Euler's relationship. But anyway, sinusoidal signal look like this. So x of t equal to some amplitude a, and cosine omega naught t plus phi. Now things are a little confusing here, because we have complex signals, so those numbers might all be complex number. But for our purpose, we actually have this omega naught and phi be real number. Okay, so those two are real number, but a can be a complex number. Okay? Because that's when we have a good correspondence to our purely imaginary complex exponential, or in other words, so we need omega naught phi to be real number for this to be periodic. Anyway, so remember that omega naught and phi are real, that will be periodic, and A can be actually arbitrary, A can be complex. Yeah. And now we kind of assume A as real, so we can plot this here. So here is a plot of the sinusoidal function you are probably pretty familiar with in high school. So you look at this going up and down. And it's periodic with period 2 pi divided by absolute value of omega naught. So once again, the fundamental period is this distance, and it will be 2 pi divided by omega naught. Okay. And here we have some wording about calculation of the unit of the things here. So usually we count our t as time, and it has unit as seconds. And this phi will have unit of angle, so the angle we usually count in radian, and omega naught will will have unit radian divided by time, so radian per second. And so the sound notation thing, we will, so instead of omega, we also sometimes write this f. So it's a little confusing. So omega is called frequency, and also f is also called frequency. But f is a frequency in different unit. So omega will be 2 pi times f, and f is frequency in the unit of cycle per second and over hertz. Okay, so that's some notation to remember. But I guess the more important thing to remember is the fundamental period here. Also has the same form. It will be 2 pi divided by omega naught absolute value. And I guess that's something you can check a picture, because the cosine function will look like this. Okay. And here is the bigger picture. Like you can check out all the detail of it back home. Okay. And as we said, we can change back and forth between the. But we're almost done. 1 minute. So I guess let's show this slide and stop. So we can go back and forth between periodic complex exponential and the sinusoidal function. And one of them is this. This is just the Euler's relationship. Right? So one side we have those periodic complex exponential. The other side is the linear combination of sinusoidal. So we have cosine and sine. Even though we only say cosine is sinusoidal, and obviously if you put sine here, it's also sinusoidal. And then we can use our reverse Euler and turn our cosine into linear combination of complex exponential. Okay, and we are right at the time, so let's stop here, and let's take a break here, and we'll come back at this slide 10 minutes later.还活着吗？希望还活着啊。这样。
现在还可以加钱吗？
现在应该还可以啊。
哦，那
如果你送，他们系统还没关嘛，所以你是今天有送的吗？还是怎样？因为我今天还没 check。
我昨天有送。
昨天有送，那我应该可以现在签。真的我忘记。
我是原本有签上，然后
有签上还被踢掉吗？这我不太确定。
我不小心记，我按错课。
哦。
就我不小心记。
好，那我可以。你是资工系吗？
对，我是资工系。
OK， 资工系我的考的是一直都加签。对，然后那我现在签一下。等一下我看一下加签系统。 这样子就不会过去了哦，这样也方便。我找一下，系统应该有给我信。加签。这个是你寄信给我吗？
对对对。
OK。找到。OK。这里还有。这个不是。看一下。3793。这里吗？还有2个。我看一下。除了你以外，还有人丢。资工系有你2年级的 ，OK。好，4年级的现在才丢 ，International OK 都同意。应该还可以。OK。
好，谢谢教授。
这样。写错了。 怎样？
问题想要问，
哦，可以啊，可以啊。
就是关于这一个哦，他说这个是找他的那个大小嘛，找他的美度嘛。
抱歉，我有看到你的说是哪里？
就关于
哦
energy 的部分，
，energy，
就是他这里要拿它的大小，
嗯哼，
是吗？但是，就我比较有点疑问的就是说，
有问题吗
如果它是那种 complex number 的话哦，
？complex number，那你还就要选 complex number 的大小。
那个美丽丢嘛，是不是？
对啊，
这样假设它 xt 是直接等于有5 cos 2t 这样子的话，
嗯哼，
然后这样子的意思是什么？就到底是具体是怎么样操作？有点。
然后我不是很懂你的问题。
假设 xt 是5 cos，
你的 xt 是就直接记成 xt 等于什么？
5 cos
这样子不是 complex 啊，但是
就假设它不是 complex，
对，那就直接算不是吗？
哦，所以是不用再说，就直接忽略那个找大小部分。
对啊，就会这样子啊。你要把它对嘛，应该是对，然后你要几分？然后一就是 whatever 一般到几度？对，我在写字有什么意思？但是那样的话就会你的 x o t 就会这样的感觉，square 就会这种感觉吧，不在 square。然后积分的时候，比如说你积这一段，然后它可能就会平均起来就减重到这个感觉。
如果 x 是1加2j 这样，
1+2j，那不是很无聊吗？上正方选。
假设这样子的话，就是
那1加2的平方就会是5啊，就是1平方加2平方等于5。
所以是有，所以是有可能是有代替的一些。
对啊，
这是没有代替。
对啊，这没有代替嘛？那你可能要比较有趣一点的，你 x o t 也就是我们刚才讲的，e to 的 j omega t 的话，写不出来。还可以。x o t 等于 e to 的 j omega t， 这样其实更好算，这样的话你就有x o t 就会是 square， 然后知道它什么？
那这里的大小的话是
这个的绝对值然后再平方嘛，但是这个绝对值是1，这个是平方会变1这样子，就跑过去。
直接找了大。
啊，那我们就
是一种这种 complex， 找到大小之后是有代替的东西。
那可以啊，是有放啊，然后随便选一个题嘛，这样子的话这就变平方对。但是不太结果啊，这个发现它泡越来越大。
就是有可能找代替，然后觉得这是
然后就几分。应该可以啊，反正我们主要是教室坐满，然后看起来就位置在对那个。对，那你是有电子系统丢给我吗？还是你还没丢？那你可能丢一下吧。你是职工系的吗？
是，我是那个学士班。
学士班，然后学士班应该可以。学士班我们应该还算 priority 对吧？但总是应该还有座位对。学士班应该还算 priority。对 anyway, okay. I think it's time to start. Hello. Okay. Let's get back to our sinusoidal signal. Okay. So sinusoidal signal look at this. So x of t equal to a cosine omega naught t plus phi, or a sine omega naught t plus phi. Okay. and this omega naught should be real because it corresponds to this omega naught here. This omega naught in complex exponential, and this omega naught is real, even though its the imaginary part of A is real. Okay, the coefficient of the imaginary part is a real number. And anyway, so here we see how to one way to decompose our this purely imaginary complex exponential into sinusoidal functions. And this is a direct application of our Euler relationship. So we break e to a j omega naught t to cosine omega naught t plus j sine omega naught t. And we just copy a c here. Okay. So from here, you see why we want the omega naught and the phi to be real. Because this is omega naught here, although we didn't see phi here. And c can be complex here, and c will stay complex here. Okay. So those are sinusoidal, and we can also do this in reverse direction. And that's why we talk about the reverse Euler before. So we have a cosine omega naught t plus phi. Then we can break this back to complex exponential. So the relationship we have here, so cosine omega naught t plus phi, then we can make this e to the j omega naught t plus phi and e to the minus j omega naught t plus phi. Then then we can break up the complex, the omega naught t and the phi part of the complex of the exponential also. So then we left with this e to the j omega naught t and e to the minus j omega naught t, and we have some complex, and we have some other. Excuse me. Yeah, we have some other complex coefficient here. Okay. So like this. I guess any question? No. Yeah. So we can look at this whole thing as another new C, and this whole thing as another new C. Okay. And another way to break the cosine and sine to complex exponential, I guess, is doing our reverse Euler in different idea. So instead of doing this addition and subtraction, we can also just say cosine omega t is just a real part of e to the j omega t, because as you see, e to j omega t, the real part is cosine and the imaginary part is sine. So we can just say our cosine omega t plus phi is the real part of e to the j omega t plus phi. And we use this relation notation, Re and the curly bracket as taking the real part. Okay. And yeah. Sometimes the font of this is not very good, but hopefully we can understand. The font sometimes is not very consistent, but this Re curly bracket thing means the real part. And similarly, we have this. Okay, now it's a bit confusing. I think it is JM. Is it IOJ? I'm not very sure, but or IM. Okay. Anyway, the IM of C means the imaginary part, and it's slightly confusing as we say the imaginary part is actually a real number. Okay. And anyway, so IM of C means the imaginary part of C. And if you take it on complex exponential, you give you this sign back. Okay. So question on the sinusoidal function. I think this is how much we talk about them for today. And anyway, the a bit more important concept here are the fundamental period and fundamental frequency. So we already defined fundamental period is defined for any function. any periodic function is remember is the smallest t such that you have x of t equal to x of t plus big T. Okay. And but when we discuss our complex exponential and sinusoidal, we see that our fundamental period for them all have the same form. So they are inverse proportional to this absolute value of omega naught. And we have their fundamental period T naught will be 2 pi divided by absolute value of omega naught. And we have a special case. Where omega naught equals to 0, we have a special case such that this big T is periodic with any T. And well, it don't quite have a fundamental period. I guess the fundamental period will be 0. But yeah, I guess we don't need the definition here. Because it's periodic for any T, big T. And but anyway, here we want to make another definition. So this is kind of circular, but actually not. So we want to define fundamental frequency for any periodic function. Okay. So we define fundamental frequency as 2 pi divided by fundamental period. Okay. And now it's circular, so fundamental period is 2 pi divided by fundamental frequency, and fundamental frequency is 2 pi divided by fundamental period. So actually the chain of logic goes like this. So fundamental period, remember we have a definition for this without having omega naught. The fundamental period is defined by the smallest t, such that the time shift doesn't change the signal. So fundamental period is the smallest period. And the fundamental frequency is defined by 2 pi divided by fundamental period. Okay. So as an example, we have a sinusoidal function here, so a cosine omega t plus phi. So suppose we don't have actually, which way do I want to do this? I should probably do the other way. It's okay, probably this is still better, although it's a little different from what I had before. So suppose we have a function a cosine omega t plus phi here, and the fundamental period, as we showed before, it should be so fundamental period t naught should be 2 pi divided by absolute value of this omega, right? This is what we show. What do we say about the fundamental period of the sinusoidal function? I guess we didn't go into detail, but you can see pretty intuitively from the picture here. So the smallest period is t naught, will be 2 pi divided by absolute value of omega. Okay? And then we can calculate the fundamental frequency. This omega naught will be, it's very confusing. Okay. This omega fundamental frequency, let's call it omega naught here, it will be 2 pi divided by t naught. And what I want to say is equal to the, it's equal to the absolute value of omega. Okay. So I want to find everything logically, then you use this relationship to find the fundamental period, then you use this relationship, so you cannot see. Then you use, unbreak. Yeah, so you use this relationship to find fundamental period, then you have 2 pi divided by fundamental period equal to your fundamental frequency. Okay, so that's how everything is defined. And back to our sinusoidal and the complex exponential, we find out that this omega naught is very related to both our fundamental period and fundamental frequency. So I guess I should still change this back to consistent with everything. So I have so this omega naught, and so let's call the fundamental frequency omega, and the fundamental frequency will be the absolute value of omega naught. Okay. Yeah. So absolute value of omega naught will be the fundamental frequency, and 2 pi divided by the fundamental frequency will be our fundamental period. Okay. Okay. And so those are fundamental frequency and the fundamental period. And here are some examples of different omega, how they change the function. And we can see that for the sinusoidal functions. So some cosine omega t with omega 1, omega 2, omega 3. So we have a higher omega, then the cosine will oscillating faster, and you see things are squeezed more inside, compressed more. So those are 3 cosines with different omega. So omega is decreasing from omega 1, omega 2, omega 3, and you can also see the period is increasing. So the period here is smaller, then period get bigger, then get bigger. Okay, just what I want to say here. Yeah. So bigger omega, higher frequency, and shorter period. I should get. Okay. Question? The quite important concept of fundamental period and fundamental frequency. Okay. Now let's check something we talked about last class. That's the energy and the power. So there is not too much to say here. And anyway, so the energy and power for our periodic complex exponential and the sinusoidal, they are pretty stable. Actually, we only check the complex exponential here. Because they are easier. Anyway, so periodic signal. So here we give a more general statement, but we only check a very special case. But you can get the idea here. So for any periodic signal, because it's periodic, so they will have a finite average value power. So I guess that's not technically quite true, but if our signal is not weird, that's true. Okay. Anyway, so it's I should say the average power over a period will be a constant, and if it's finite, then it will be finite. And so it will be a signal with usually it's finite average power, and as a discussion before. Then the total energy, because total energy comes from time negative infinity to positive infinity. So if a finite power times infinite time, you will have infinite total period energy. Okay. So nothing too special, but we can calculate basically the power of our complex exponential. Then we see that the power is this e to the j omega t absolute value square. But e to the j something absolute value is just 1, so the power is 1. And so the energy over a period is just the length of a period, and the average power is just as the instantaneous power is 1. Okay. And so the power over 1 period is 1, and power over the infinite interval is still 1. And as we said, the total energy, if you integrate this from minus infinity to infinity, then the total energy become 1 times infinite, and it become infinite. Okay. So nothing too special. Okay. Question? Okay. Now let's back to go to quite an important concept. This harmonically related complex exponential. So basically, we want to study what exponentials. So what are the complex exponentials that has a period t0? Okay. So obviously, if your omega equal to 2 pi divided by t0, so something kind of feel like this, although we are drawing the sinusoidal, so I guess we are drawing the real part of this e to the j omega t, or imaginary part. Anyway, so we want this to be periodic to big T, then this will be periodic to big T. Right? So this is like a sine omega t. And but as we say, remember before we say, if something is periodic with period big T, then it's also periodic with period 2 big T. So actually we can have, so if we want to shift that statement around, then if something have a double frequency, it's also periodic with period big T. And we triple the frequency is also periodic with period big T. So actually there are a lot of complex exponential that has big T as one of its period. So there are, so big T, so this big T0 is not the fundamental period for those things, but it's still the period for them. Okay. So here's the idea. But here we kind of shift the perspective. We already fixed this T0 here, and we want to find everything that has big T0 as one of its period. So basically, their fundamental period would need to be a fraction of this big T. And we solve those in equations, we will see the same thing. So we want some omega such that e to the j omega t0 equal to 1, because that's e to the j omega 0. And then that means that this omega t0 need to be integer multiple of 2 pi. So it is 2 pi k being some integer. And if we shift things around a little, and also define omega naught as this 2 pi divided by t naught, then we just shift the t naught here, then you see that omega should equal to omega naught times an integer. Okay, so yeah, so that's the solution. So harmonic related complex exponentials this e to the j omega t, this j e to the j omega t with those omega. So e to the j k omega naught t. And so you see their frequencies are integer multiples of this omega naught that correspond to t naught. Omega naught equal to 2 pi divided by t naught. And those complex exponentials are called harmonically related complex exponential. They are harmonically related because they all share this big period t, big period t naught. And harmonic actually come from music terms, because people want to use harmonic frequencies to compose their music, their songs. And anyway, this will be an important concept, because when we study periodic signal with some period t, because so spoiler for the later part of the course, we'll see that whatever signal with period t, so maybe a signal with a really weird shape, they can always be decomposed into the sum of those harmonic complex exponentials. So e to the jk omega t with all the different k. Okay. So that's why we want to talk about it here. Anyway, here we see that we have this integer multiple of e to the jk omega naught t. Then they all share the same period, big T. Any question? Yeah. So I guess one thing about this complex building block. So because all those functions has big period big T, you see that you add them together, they still have the period big T. Okay? And but we'll later show is the converse of that statement. So adding them together will give something periodic in big T. And actually anything periodic in big T can be decomposed into linear combination of that. Okay. And that's basically that. Oh, so something special. So k equals 0, then once again we have a degenerate case of set k equals to constant. And so that's periodic with any period. But for other k, then then our set k of t has fundamental frequency big K, K absolute value times omega naught, because we define omega naught as positive value here. And yes, so the frequency will be integer multiple omega naught, and the period will be a fraction of t naught, as we said before. Okay, you can see here. So the omega is twice, 3 times, and t is 1/2, and 1/3. Okay, so those are harmonics. Well, it's so slow. Should be fine. Okay, and okay, so let's run through this a little faster. So now we consider this function, and we can think about what's its fundamental period. So it has 2 parts. This is J2t, and another part J3t. Then the first part has fundamental period 2 pi divided by 2 equal to pi, and the other part is 2 pi divided by 3, 2 pi over 3. And okay. And we want a fundamental period for both of them. Then basically you want to find the least competent multiplier for those two things, and that is 2 pi. Okay, so you want to be a multiple of pi and a multiple of 2 pi divided by 3. Then it's this thing. And the other thing we want to show here is you have a function like this. Then we can write it in terms of sine and cosine to plot it, to make an easier plot of this. So you have e to the j2t, e to the j3t. Then we can take all the e to the j 2.5 part. Then this becomes minus 0.5 and plus 0.5 here. Then we can apply the reverse Euler here, and we see this is cosine 0.5t. Okay. And then we can express the magnitude of this easier. Yeah, so we take the magnitude of this thing. Then if you take absolute value, then this e to the j 2.5t part become 1, and just absolute value of cosine 0.5t, and you can plug it like this. Okay, question? Okay, not. Then let's go to general complex exponential signal. They're actually not that much interesting because they are hard to use, but we can write them in more intelligent, kind of more analyzable forms by choosing good decomposition of C and A. Okay. So anyway, so if our C to AT has general form, then C and A are both complex. And we want to express C in polar form and A in this rectangular form or Cartesian form. because if we do that, then you see so e2 c equal to the absolute c e to the jc. Oh, actually it's j5 here, but whatever. So it should be j theta here, right? So it should be theta. And anyway, c equal to this and a equal to this, then we can pull things apart. So then we separate this e to the rt outside, and we can kick this e to the j theta inside. So we get a form of the complex exponential with something linear to t. So we have omega naught t plus theta. And now we have a real exponential, who will be exponential growing or decaying. And now we can also separate this to real part and the imaginary part to make the plotting easier. So now this e to the j omega naught t plus theta become cosine and j sine. And now we plot the real part, then it's cosine times the exponential e to the rt. So it's either exponential growing or exponential decaying cosine, depends on whether your r is bigger than 0 or less than 0. And it will just be similar for the imaginary part. So it's also exponential growing or decaying, depends on whether r is bigger than 0 or less than 0. Yeah. So yeah, when we write C and A in polar form and the rectangular form, you can see that you can group things into this recognizable part. So you have this absolute value C times e to rt as the amplitude of the function, and then we have the complex exponential. This is like a circular part. This periodic part that we know before, but because we are multiplying with this e to rt, so this is not periodic anymore. So it's either exponential growing or exponential decaying. Okay, so that's the general exponential. And now let's talk about discrete and complex exponential. Okay. So it's kind of similar, but we are going to see there are different parts. So as a comparison, so for discrete time, we have x equals c e to the at. And for discrete time, we have we change the notation a little bit, so we can have x of n equal to c e to the beta n. And we do something that we would like to do a lot when we talk about discrete signal. That is, we will group this e to the beta and call it another number, another name. And this makes sense because those n only take value at integer points, as you are going to see. So we call this e to the beta as just another number alpha. And so we can parameterize our discrete time signal as c alpha to the n. Okay, this is just, for now it's just changing the notation. We call e to the beta, which corresponds to e to the a here, as alpha. And because this c and the beta in general can be complex, and c to c and the alpha will also be complex. Okay, so no, nothing changed yet. But now see the real case. Now you can see things are a little different. So if c and alpha are both real, then well, c doesn't quite matter. But for different alpha, we will see different things. So if alpha is bigger than 1, you have this growing thing. If alpha is bigger than 0 and less than 1, you have this exponential decaying thing. But what's funny is now we can have alpha negative. Okay? If alpha is real but negative, So if negative, then but still bigger than -1, they have a decaying thing, but because alpha is negative, so for every n you will flip up and down, because for every n you will get the extra negative sign, right? So for alpha negative, we will have this very quickly oscillating up down and decay. And now if alpha is less than -1, so it's still negative, so you still have this up down, but the kind of exponential growing because its absolute value is bigger than 1. Okay. So you see this up down thing is not something you will see in the continuous time real exponential, right? It is only when you are talking about discrete time case. Okay. And okay, but the real cases are kind of just a showcase. As in the continuous time case, the thing we care most about is about periodic signals. So it was back when A was purely imaginary, and here that means beta is purely imaginary. And that doesn't mean A is purely imaginary. That means A equal to, means A equal to some J omega naught. And I guess a better, more succinct characterization that means the absolute value of A equal to 1. Okay. So the special case where beta is purely imaginary, and that corresponds to alpha has absolute value 1. And in this case, x of n can be periodic. But as we'll see, there are many tricky points. But anyway, those are the special case we consider now. X of n equal to c e to the j omega naught n. And we can also decompose this to sinusoidal. Say, yeah. I guess it's a bit confusing. If we write c in polar form, then x of n will be this thing. So we can kick the sum of the phase up to this exponent. And if we take the real part, you will see a sinusoidal function, this cosine here. Okay? And as before, you can change back forth between the exponential and the sinusoidal. This is just the same thing. So so basically just change t to n. So exponential e to j omega naught n to cosine plus j psi, and the cosine equal to e to the plus j omega minus e to the minus j omega, etc. And that's the sum of the plot. So here we plot the sinusoidal because once again it's hard to plot complex exponential. So here we have cosine 2pi divided by 12n, and cosine 4 times 2pi divided by 31n, and cosine n divided by 6, like this. So you see they are oscillating with different speed. And this one is nicer because you can kind of count the period here. So 2pi divided by 12, so the period is 12 here. So 1, 2, 3, 4, 5, 6. Wait, I cannot count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's one period. Okay. And just like in the continuous time case, you can write the general case of e to the c, of xn equal to c alpha n. So if it should be alpha here. Okay. If c and alpha are both complex, then you do the same decomposition. So c into polar and okay. Because we are talking about alpha and not beta here, so we make c and alpha both into polar, and then you can still write into this Next thing. So you get absolute value C, absolute value alpha to the n cosine, and absolute value C, absolute value alpha to the n, and sine, j psi. And you see the real and imaginary part are growing or decaying sinusoidal, depend on your absolute value of alpha. So absolute value alpha is bigger than 1, then you have this growing exponential. And absolute value alpha is less than 0, you have this decaying exponential, and with sinusoidal inside this cosine omega n. Cosine omega n. Okay. Okay. Now we have about 15 minutes to talk about the important part here. That's the periodicity property of those discrete and complex exponential. And we kind of skip over this, gloss over this. But the periodicity of those complex exponential is very different. So once again, it's this, e to the, so this pure beta being pure imaginary, and alpha equal to e to the j omega naught n thing. Its periodicity is very different from what we know from continuous time. So in continuous time, so the first difference when we have continuous time, we have e to the j omega t, and as we say, if you have higher omega, then your signal will oscillating faster. But that's not true for discrete time signal because you only take integer values. So for example, if you change your omega naught to omega naught plus 2 pi, then your signal, your e to the j omega naught plus 2 pi n, and then you do this arithmetic, then you see because e to the j, you get a trifactor of e to the j 2 pi n, but e to the j 2 pi n is just 1. So you back to the same signal e to the j omega naught n. So you find out that if you increase your frequency from omega to omega plus 2 pi, then your signal doesn't change. So it's not oscillating faster, it's the same signal. Okay? And this effect you can apply many times or even negative times. So if omega plus minus plus any 2 pi k, with k being integer, your signal doesn't change at all. This is a very important concept for discrete signal. So your frequency is kind of periodic, because if you change your frequency with a multiple of 2 pi, your signal doesn't change at all. Okay? And because if you plus or minus your frequency with any 2 pi, then the signal doesn't change. So we only need to think about omega, this omega naught in some interval of 2 pi. Okay? And interval of 2 pi, there are two conventions. So it's either looks natural, so it's either omega naught from 0 to 2 pi or from minus pi to pi. And as we said, when we increase omega naught, now the signal doesn't oscillate faster, because if we add 2 pi, it doesn't change, the signal doesn't change at all. So what are the oscillating faster regions? So these kind of low frequency regions are around omega naught equal to 0 or plus minus 2 pi. And the high frequency region, where you think the signal looks like oscillating very fast, is around this odd multiple of pi. So plus minus 2 pi or plus minus 3 pi. And you can kind of feel it here. So when your omega naught equal to 0 or 2 pi, all those things, then it's very close to a constant signal, e to the j0n equal to 1. And if you are around the high frequency regions, then you have e to the j pi n, and your signal will be minus 1 to the n, so kind of in the so your signal will just oscillating up, down, up, down, up, down, up, down for everyone. Okay. Yeah. And another difference here, also kind of why we have the quotation here, is that this e to the j omega n is not even periodic. for a lot of omega naught. Okay? That's very different from the signal e to the j omega t. So in continuous time, e to the j omega t, as we say, is always periodic. But e to the j omega naught n is not always periodic. because because when we calculate the period here, it's like 2 pi divided by omega, right? But remember the period, this big N for discrete signal, always need to be an integer, but 2 pi divided by omega naught might not be an integer. So it can be not periodic for a lot of omega naught. And okay, so that's a little misleading, but anyway, let's see the actual math. Okay, so if we want this thing to be periodic, then we write down this periodic equation. So e to the j omega n plus big N equal to e to the j omega naught n. Okay, and we do the usual cancellation, and we see that e to the j omega naught n equal to 1. Okay. And as before, that means that this omega naught n should be an integer multiple of 2 pi, and that's called our integer m. So omega naught n equal to 2 pi times m. And what does that mean about omega naught? That means if we will move things around, omega naught n divided by 2 pi, it would need to be m divided by n. And now remember, m is an integer and n is an integer. So we see that omega naught divided by 2 pi need to be a rational number. Okay. So actually there is only small number of omega naught give you a periodic function. Okay. Omega naught need to be a rational multiple of 2 pi for your signal to be even periodic. Okay, any question here? This is the important concept here. Okay, and okay, and the n is the fundamental period here. I guess the smallest n you can find here is the fundamental period, and the fundamental frequency once again will be 2 pi divided by the fundamental period. And that will be omega naught divided by n. I guess we are doing this in reverse order for whatever reason. But the fundamental period will be m times this 2 pi divided by omega naught for the smallest possible n, because we want the smallest possible n. And then we can have the fundamental frequency being 2 pi divided by n naught, and it will be omega naught divided by m. So the fundamental frequency will be different from omega naught for most of the time when m is not equal to 1. Okay, yes, will be a short downtime, but still let you look at this. Okay. So the thing is, we will want to calculate omega naught divided by 2 pi and see where it's a rational number. If the rational number, we find the smallest fraction m and n, and we can calculate n here and calculate the fundamental frequency here. So here are some examples with picture. So we plot cosine omega naught t. So we change omega from 0, 1 over 8, 2 over 8, so all the way to 16 over 8, etc. And this is continuous signal. You see that when you increase the omega, your signal are oscillating faster and faster, faster and faster. But now we go to discrete signal, and we still increase the omega. So it goes this way. So you see that the beginning is what you expect. So your discrete signal is oscillating faster and faster when you increase the omega. But when you reach really high omega, so those omega naught around around pi, then you see your signal kind of look weird. you see that when you at omega naught equal to pi, then your signal becomes this up down thing, and this is the highest frequency you can see in your discrete signal. And when you increase your omega naught faster, then your signal kind of goes back. You see this signal look at this signal, right? And yeah, and you see that when your omega naught reaches 2 pi, then the signal actually becomes constant once again, even though when continuous time is oscillating phase very fast. But in discrete time, you don't see this oscillating phase, you just see the constant function. And you increase your omega naught even more, then this whole thing repeats. Okay. Yeah. And here we go to 4 pi, and you see. So here we go to 3 pi, and you see, once again, this is a high frequency thing, and go to 4 pi, and you see it goes back to constant function once again. Okay? So this is a very different property for discrete time signal. And we are really short time, but let's try to run this example, see if people want to answer. So those are 3 functions that we've seen before. 3 discrete time complex exponential we've seen before. So x of n equaled, not complex exponential, sorry. So it's cosine 2 pi over 12n, cosine 4 times 2 pi over 31n, and cosine 1 over 6n. And if we have a continuous time, then their fundamental period will be 12, 31 over 4, and 12 pi. And what if discrete time? So discrete time will recount this. So for discrete time, the period here is still 12. Fundamental period here is still 12. But is the fundamental period here 31 over 4, and is the fundamental period here 12 pi? So I guess raise your hand yes or no. You think the fundamental period is still 31 over 4, raise your hand. If it's not, raise your hand. Okay. And okay, so for those of you raise your hand, so what's the fundamental period here? Anyone want to answer? Okay. And anyway, okay. So it's actually, the spoiler is actually 31, because we want to look at this as a fraction, right? So we want to find the smallest multiple of this that's an integer. So the fundamental period here is 31. And I guess this question now is easier. So if this is the fundamental period, raise your hand. And if it's not, raise your hand. And anyone who answer what's the fundamental period here? Shake your hand. Shake your hand as your answer or as you don't know. And anyway, so this is not even a rational number. So this is not periodic. So I assume those shake your hand has the right answer. Yeah, and we are on time, so I guess you can read this, but here is a summary that you want to calculate this omega naught divided by 2 pi and see where it's rational, and you can calculate the fundamental period and the fundamental frequency there. And if it's not a rational number, if omega naught is not a rational number of 2 pi, then your discrete signal is not even periodic. And we have a table here. Okay, that's for today. And we'll have a homework all sometime today. And yeah, see you next Tuesday.